All right, this is lesson 1 of Unit 4, and today we'll be talking about finding critical values of a function. A critical value of a function is any x value, we'll call it c, so that when you plug it into the derivative, either the derivative is equal to 0 or the derivative is undefined. And what we're going to find is that critical values are important because they are places where a function could change direction, doesn't have to, but we'll see some examples here. And that's going to help us decide when a function is increasing or decreasing, which we will use to find minimum and maximum values later in this unit. Okay, some examples of what it would look like for a derivative to equal 0, right? So that would mean the slope of the tangent line would be 0. And so examples would look something like this. Right? This could be our c value. And you would have a tangent line with a slope of 0. Okay, could go the other way. Something like this. And so we see that, this is changing direction, right? Increasing to decreasing. And this goes from decreasing to increasing. But it doesn't have to change direction. So another example would be, okay, something like this. Just like a cubic kind of a shape. And this would go from increasing to increasing again, but in the middle here, there would be one place where the slope would be 0. Okay, so again, why are critical values important? A function could change direction at a critical value. And that is going to be a big idea that we're going to keep coming back to throughout this unit. Okay, we also said that a critical value could be a place where the function is, or where the derivative rather is undefined. When we say f prime of c is undefined, another way of saying that is f is non-differentiable at x equals c. Right? We're not able to find a tangent line, and we talked about this, feels like quite a while ago, but we'll remember that a function is differentiable if it is continuous and smooth. Okay, so this would be an example of something that is non-differentiable. Okay, this would be a place where the derivative is undefined. A hole, a gap, an asymptote, right? These would all be my c value. And, here, right, this thing is always increasing. But like in this example, we went from increasing over here to decreasing on this side. So again, the function could change direction at a critical value. All right, this one again went from increasing to decreasing. Okay, one other way that the function could have a derivative that's undefined would be a cusp point. We talked about those before. Okay, or like an absolute value function, right? Same idea. Those would also be places where the derivative is undefined, and yet we can see, again, it's changing direction. One final thing that can happen, and I don't want you to worry about this too much because it doesn't happen that often, is you could get a vertical tangent line. And of course, the slope of a vertical line is undefined. So we also say the derivative is undefined. Okay, so that's what it looks like. Now for today, don't worry so much about, how am I going to know what my graph looks like? That is what the rest of the unit is going to be about. For today, we are simply going to find critical values. We're not going to do anything with them yet. Okay, so the process that we're going to go through today, to find a critical value of a function, we first obviously take its derivative. And then at that point, we think about, could the derivative be undefined? Usually no, but sometimes yeah. And then we set it equal to 0 and we solve. And I'm going to go through 4 examples right now that will help you to do the homework examples on your own. All right, so we'll start with the first example. This is a fairly easy one to get us started. Okay, we're given this function. The directions are find the critical values. And so we'll take a derivative. Okay, that's why we spent a long time practicing derivatives. So now that hopefully that's the quote unquote easy part of this problem. Could this ever be undefined? Okay, well, no, it's a polynomial. right? Really what you're looking for is, are you dividing by 0? 0. And obviously, in this case, there's nothing you could plug in that would ever cause that, so that's not going to happen, so you don't need to worry about that. But you do need to ask the question every time, because if you don't do it when it doesn't matter, you're going to forget to do it when it does matter. All right, so now we just go right to setting it equal to 0. Okay, and this is why you took Algebra 2, so that you would know, hey, I can factor, and I know my answers are going to be 0 and 2. Okay, and those are my critical values, which you can just call CVs if you want. And for today, you're done. Right? Later in the week, we'll be doing things with these critical values, but for today, that's where you would stop. All right, another example. Here we're using trigonometry. Okay, and they're giving us an interval because otherwise we would get an infinite number of solutions. Okay, so we take a derivative. Derivative of x is 1, and then sine becomes cosine. Could this ever be undefined? Well, no, we know the graph of cosine, right? Cosine is just this nice, it just goes on forever and ever. No holes, no gaps, no asymptotes, so no problems there. So no, this thing can't be undefined. We're all set there, but we're going to set it equal to 0. Okay, and this, this is part of why you took pre-calculus, is to know how to be able to solve this kind of thing. So we need to get cosine by itself. Okay, and if you do that, you will find cosine equals 1/2. And this is where you need to know your unit circle, because you wouldn't have a calculator, probably. Okay, so that's going to be this location and this location, better known as pi thirds and 5 pi thirds. And for today, again, just stop right there. All right, a third example. Sometimes our derivatives just get a little more complicated. Okay, x squared times e to the x. First, we'll take a derivative. Okay, but let's not forget to use product rule. Okay, so we end up with this. If you're still having trouble with product rule, quotient rule, etc., get help as soon as you can with that, please. All right, now could this be undefined? Okay, well, we don't have to worry about the x and the x squared, so maybe the only thing you're concerned about is e to the x, so this is where it's helpful to know what that graph looks like. E to the x just looks like this. All right, it's exponential. It's never gonna blow up, it doesn't have asymptotes, so we're all set. Okay, that's not gonna be undefined. But we could set it equal to 0. Just getting rid of parentheses now. All right, so now we just, we need to think a little bit, and this is where factoring is always a good idea if we can. So I notice, hey, these both have an e to the x, so maybe I'll pull that out. And then, you look and, oh, well, these both have an x, so I could pull that out as well. Okay, and of course you could have done that in one step. All right, now when you have multiplied things, you can set them equal to 0, so you end up with e to the x equals 0, x equals 0, well, so that's just an answer, and 2 plus x equals 0. Well, that's easy. Okay, x equals -2. So then you might not be sure about this part. But this, again, is where it's helpful to know what the graph of e to the x looks like. There's an asymptote here, right? All exponential functions have that asymptote. And so this is going to get closer and closer to 0, but it's not going to touch. This actually cannot happen. This part just has no solution. The other way to think about it is if you took e to the x equals 0, if you were going to try to solve that, you would take a natural log of both sides. Okay, that would cancel out to just x, but the natural log is undefined at 0, so we can't do that. Okay, there's no solution. So your critical values are 0 and -2. All right, final example. And this one will be a little trickier, so please pay attention to this one. The first thing we're going to do is not take a derivative right away. We're going to simplify this first. Okay, this is something we're going to have to get used to because, last chapter you just took a derivative and you didn't do anything with it. So it didn't matter if your derivative was kind of complicated, but now we're going to set things equal to 0 and we're going to need to solve. So you'll get used to doing this. The more you can simplify something before you take a derivative, the easier things are going to be. And so, in this case, we could split this up like so, right? When we have, things being added or subtracted over a denominator, we can split the fraction. But then that cleans up, right? We can cancel an x, so we get x squared over 2. And then we can cancel these 2, so that just becomes 1 over x. Now that is still f of x. And I'm just going to move the 1/2 in front, right? Just to make things even easier. We have not taken a derivative yet. You are simply, manipulating it, doing algebraic things to get it in a better form. So be careful. Some students they think like, oh, I did some work, so I've taken my derivative. So just be careful. Okay, now we find f prime. And look how much easier this is going to be. Now the 2 comes down, right, cancels out with the 1/2. So that derivative is just x. And then, if you forgot, think of this as x to the -1, right? So that's going to be negative x to the -2. Okay, so I'm just going to rewrite that as -1 over x squared. Much better than doing quotient rule. Trust me. Go back and try this example with quotient rule and you'll see what I mean. All right, now, could this be undefined? Yeah, that's okay, different than all the other examples. We have this going on, right? So we could divide by 0 here if x equals 0. That's going to cause a problem. It also causes a problem in the original thing. We could have noticed that too. That is a critical value. We need to consider that. I'll show you why in a minute. Okay, that's the only thing that can make this undefined, though. So now we go ahead and set this equal to 0. Okay, and then we just need to be a little clever. How do we solve this? So the easiest thing to do is just add this thing to both sides. Okay, so we get 1 over x squared equals x. And then we could multiply both sides by x squared. And so that cancels. And that gives us x cubed. And x cubed equals 1. Well, that's obviously x is 1. Okay, that is also a critical value. So this is a critical value, and this is a critical value. And they're both important. And, later in the unit, we're going to do things with both of those, and we'll understand what's happening. Just to show you what's going on with this graph, if you were to graph this original function, it looks like basically like this. I don't know the exact graph, but something to this effect. Okay, there's an asymptote at 0, which is why the derivative is undefined at 0. Okay, and then the graph turns around at x equals 1, which is why we find the derivative equals 0 at that location. All right, so these 4 examples should hopefully give you enough to do the homework. If you look on Canvas, I started a new unit, okay, unit 4, and I'd ask you to try your best with the assignment. I am going to check it on Wednesday just to see how you did and to give you a homework grade for the second quarter. If you have any questions, email me anytime, and I hope this was helpful. I will see you on Wednesday.